13.5, changing equilibrium conditions, Le Chatliers principle, my favorite principle. So what we have is we have a system that has reached equilibrium. Okay, so it's in equilibrium, the concentrations aren't changing anymore, or the pressure, if we're talking about gases, the partial pressure isn't changing anymore, all right? And then we do something to it to make the reaction shift either towards the reactants or the products. Okay. Now, one thing to keep in mind, K only changes, so the value of K only changes with a change in temperature. And we'll talk about that more in a little bit here. So in other words, in all of these situations, K is going to remain constant, and what we're going to be talking about are what does the system do in order to maintain that value for K. Right. So Le Chatliers principle. A system under stress will shift to relieve that stress to regain equilibrium. Let's throw that in there. Okay. So as I said, the equilibrium constant remains the same value at the same temperature. And changing these conditions are going to shift the reaction so that that equilibrium constant remains the same value. Right. The first one we're going to talk about is a change in concentration. Right. Now, the important part here is identifying the stress. In other words, what's making the system go out of equilibrium. So here, take a look at this one. We've got hydrogen. I'm just going to rewrite it here. Plus iodine forms 2-hydrogen iodide. Okay, now this system has reached equilibrium. So in other words, the concentrations are such that when I solve for them, it equals that value for K. So I have a certain ratio. Well, I add some extra hydrogen. So now I have twice as much hydrogen as what I should have at equilibrium. So the stress here is too much hydrogen. That's the stress. So how do I get rid of that stress? Well, the stress is too much hydrogen. I need to get rid of hydrogen somehow. Well, the way that I get rid of hydrogen is I shift to form HI. Because when I form HI, I use hydrogen. So I'm going to end up forming more HI. I'm going to decrease my concentration of iodine. I'm going to decrease my concentration of hydrogen. And I'm going to continue to do that, form HI, decrease those other concentrations until that equilibrium value equals K again. Okay, now, we're not asking you how much does it shift. We're just asking you which way does it shift. In this case, it shifts to the right. It shifts to the right to shift to the products to get rid of that hydrogen. But what if the stress isn't too much hydrogen? What if the stress is not enough hydrogen? So I've let it reach equilibrium, and then I've done something to remove hydrogen from the equilibrium condition. What's the stress? Well, the stress is obviously not enough hydrogen. So I need to form more hydrogen. So then I'm going to shift to the left, because if I shift to the left, HI breaks down, forming hydrogen. So I'm relieving that stress by making more hydrogen. So again, it's going to shift to the left. What if I add HI? So now, similar stress to what we've seen before. So I add HI gas, right? So what's the stress? Too much HI. How do I get rid of it? I shift to the left. I shift to the left. I shift to the reactant side to remove the excess HI, hydrogen iodide. Okay, and then of course, if I remove HI, what am I going to do? I'm going to shift to the right. So there's a bunch of practice problems on this for video problem 76. So make sure you go and check those out. All right, so that's concentration. Let's talk about a change in the volume of the container. So in this case, I've got some container, right? So here's some container, and inside that container, I have this movable piston. So this piston can move up and down, and that essentially changes the size of the container. Right? Now, a shift in the volume of the container, a change in the volume of the container, only affects gases. Right? So if these are all aqueous, changing the size of the container has no effect. But since they are gases, changing the size of the container does have an effect. Right? So if we decrease the volume, in other words, I take this and I push it down here, which decreases the volume of the container, right? So the stress is not enough space. So what we're going to do is we're going to shift so that we take up less space, right? So think about it this way. Here are, it's just two spheres, right? That have taken up a lot of space. If there's not enough space, can't I make this do that, which takes up less space? We're going to shift to take up less space. How do we do that? Well, we know that 1 mole of a gas takes up 22.4 liters of space. So if I have 3 moles of a gas on this side and only 2 moles of a gas on the product side, well then 2 moles of a gas will take up less space than 3 moles of a gas. Right? So if I decrease the volume so there's not enough space, I'm going to shift to the fewer moles of gas. And then vice versa. If I go from this spot and I increase the amount of space that I have, so I increase the volume of the container as such, well now the stress is too much space. So now I'm going to shift to the left in this equation to the more moles of gas in order to take up more space. All right? A catalyst has no effect on equilibrium. It will make us reach equilibrium faster, but it does not affect the concentration or the partial pressures in order to reach that equilibrium. Okay, it just makes us reach it faster. Okay, and the final one, and this is temperature. Now remember, temperature is going to change K. And we can talk about that here too. But an increase in temperature favors the endothermic reaction. Okay. Now the reason why is because energy, in this case, if we increase the temperature, the stress is too much energy. Right? So how do you get rid of energy? Well, you don't give it off, because if you give it off, all you're doing is merely heating up the area directly around you. Instead, you take that energy and you store it, and that's what an endothermic reaction does. It absorbs energy and stores it in the reaction. Right? So notice that this is an endothermic reaction, so delta H would be positive something. So if I increase temperature, it's going to shift to the right, and that's going to favor the endothermic reaction. Now, what actually happens to our value of K? So if I increase the temperature, I am going to shift to the right, forming more products. K gets bigger. So I can make that prediction. Why does K get bigger? Because I get more products and fewer reactants. So this number gets bigger. These numbers get smaller, which means that my K is going to get bigger. Okay, because remember, K is products over reactants, if you can read that. All right. Here's an exothermic reaction, so that's negative something, right? So in this case, if I increase temperature, it's going to shift to the left. Right, because if the forward reaction is exothermic, the reverse reaction is endothermic. So in this case, K is going to get smaller, and basically for the opposite reason. Okay? So that's Le Chateliers principle. Go on over, take a look at the video problems, and you'll be in good shape.